So let's get started. Welcome everyone to this special seminar. So this is a joint seminar between the Data Science Institute, as well as the Department of Electrical Engineering. Welcome, and it's my great pleasure to introduce our speaker, Nick Lane. So Nick is a professor in the Department of Computer Science and Technology and a fellow of St. John's College at the University of Cambridge. He also founded the Cambridge Machine Learning Systems Lab. Nick is also lab director at Samsung AI in Cambridge. It's a 50-person lab focusing on different various open problems in machine learning. He's also leading a team focusing on distributed and on-device forms of learning. Nick received many awards, including Best Paper Awards at IPSN and UBCOM. He is also a recipient of the ACM Census Test of Time Award, as well as the ACM SIG Mobile Test of Time Awards for his pioneering research. Nick was also the 2020 ACM SIG Mobile Rockstar awardee for his contribution to the understanding of how resource-constrained mobile devices can robustly understand, reason, and react to complex user behaviors and environments through new paradigms in learning algorithms and system design. So I guess also, Nick was part of Microsoft Research Asia a long time ago. So it's great to have you here. And with that, I want to pass the microphone to you, Nick.
Thank you, Fred. That was a very kind introduction. And it doesn't seem that long ago that we're in Microsoft together. And I always remember those times fondly. So it's always great to be back, even though it might be virtual, back seeing you. So, so with that, thank you very much for the invitation too, to speak to you all today. What I want to do is discuss with you the interesting things we've been doing lately in the area of distributed machine learning. And the way I want to enter into this topic is to motivate why we're so interested in this form of machine learning. And so I've got this sort of rather provocative title here, Machine Learning in the Data Center, a Dangerous Dead End. And so what I want to do is begin by defining what do I mean by machine learning data center, and then unpack this dangerous dead end property that I see and that's motivating us to study alternatives. So to be clear, when I talk about machine learning and data centers, I'm talking about a very specific, although ubiquitous form of machine learning that we all encounter today throughout our daily lives. So if you are searching the web, maybe looking for images, if you are interacting with a device like an Alexa in your home, every time you use your smartphone, almost all of those services are operating in the way that is being illustrated in the middle here, where we have these large data centers that have been purpose-built to maintain, train, and serve inferences from these large neural nets that are trained on largely heavily curated, static, although relatively large data sets. And this is a paradigm in which it's very hard to escape right now. And so what I believe is that in a few years' time, and it's hard to say how many years that will be, but it might be 10 years, it could be as little as 5 years, we're going to look back to this period of time when we launched and sort of used our machine learning in this way, and draw parallels to other types of societal behaviors that we pivoted away from. And so I think there will be parallels drawn in the future between machine learning and the way we use it in the data center today and things like smoking. There was a time in the 60s when doctors recommended to people they should smoke. They thought it was fairly healthy. And that's because they didn't, well, there's a variety of reasons why that was the case, but one of the reasons was that they did not know any better, perhaps. And so smoking is an example. I think that there'll be a parallel drawn between smoking and data centers and machine learning. Similar example would be lead in paint. There was a time, certainly when I was growing up in New Zealand, there was a time when lead paint was used to decorate homes And then later on, we realized there were, enormous negative externalities on the folks who lived in those homes. And so as soon as it was possible to pivot away from that technology, we did so. And there's many examples today that we haven't quite managed to get rid of yet. If you think of this way that we interact with the environment, you think about the damage through climate change, those are clearly societal behaviors that we know that we want to stop, but we haven't quite managed to get away from yet. And so the point I'm drawing is that the way that we combine machine learning and data centers today, I think will go throughout history as having heavy negative externalities that were not initially realized in terms of in terms of the ramifications for the systems that use them. And so let's unpack this a little bit more and explain why it is potentially dangerous, why it is also a potential dead end for many of the types of machine learning systems we want to construct. So one of these issues is to do with user privacy and control. Once you build a system that's premised on the idea of centralizing all the data, you're reducing the agency of the user. It's very hard for a user to know what's going to happen to their data once they've given it to a third party to collate it. And that's unavoidable if your paradigm is such that you need to have all the data in one place. And so there's a big issue with user privacy and control. There's also a big issue towards the safety of the systems that you might build on top of these types of machine learning. And so if you think about robots, if the intelligence of a robot exists inside a model, a machine learning model that only can run and only can be trained in the data center, then as soon as the connectivity between that robot and that data center goes, then the ability of the robot to react to its environment and so on is stopped. Similarly, if you have like devices such as medical device that's being illustrated here that use that listen to, in this case, they listen to heartbeats and diagnose conditions. And again, if you have a device that's mission critical, and it's the intelligence of it is located elsewhere, that severely constrains the kind of reliability of that system. Another aspect that perhaps doesn't receive enough attention is when you turn your attention to why machine learning is biased in various ways. Well, part of the reason for that is the reliance on heavily curated static data sets. Because by its nature, if you're setting out to train your models and saying, I need to drive them using data sets such as ImageNet or others, where the way that we build these data sets is through careful collection, systematic collection, careful cleaning, curation, and labeling, then that data set is always going to struggle to scale and represent all of the real world and all of reality. Because that's, even though these data sets can be huge, they can never encompass all of the examples that we're going to see. If you think about all the diversity we see in faces of various kinds with different type of ethnic backgrounds, different shapes all across the world, it doesn't matter how big your data set is, it's going to struggle to be able to capture all of the complexity of even a simple, even a relatively simple phenomena such as a human face. And so that says nothing if not when we start to expand to more complex machine learning tasks, again, that the ability of these data sets, no matter how big they get, to bridge into being able to capture all of the real world, they're going to struggle. And because of that, they're always going to have an inherent bias to them because there's some parts of the world they're not going to be able to capture. And so fundamentally, if you're building your models in this way, that relying on data sets in this way, you're going to have this property as well. Another big externality that perhaps awareness of is starting to grow is that of carbon footprinting. And so we now know that the training of these models can be extremely heavy in terms of the carbon footprint that they generate. And so many of you would have seen papers such as this one that I'm showing the figure from on this slide here, that's taken from the domain of NLP. And they realized when they did the analysis that a state-of-the-art NLP model, when you throw in all the bells and whistles, if you have a big transformer, if you use AutoML to tune all those parameters, and then you train it just once, then it's very easy to find examples where that training of that one model takes as much carbon as it takes to drive 5 US cars for their whole lifetime. And so I guess the main point, we can quibble over like how you get to these numbers and whether how accurate they are and so forth. But what's inescapable is if you train your models saying that you want to have extremely large models where you're going to have a lot of co-located heavy compute that is going to draw a lot of energy, it's going to need a lot of cooling, you can have these huge carbon footprint qualities. So where should we go to next? If all of these sort of externalities I'm talking about here that are associated with the existing paradigms, existing kind of setup of having data centers with their big models being driven by static data, a reasonable question is that if you don't like that, where do you want to go next? And so there are a few options. Up until recently, up until about 3 or 4 years ago, my group was very interested in a type of learning called on-device machine learning that addressed some, but not all of these issues. And so the idea here is that you train the model in the data center, but then you manipulate that model to lower or to shape its resources such that it can run at inference time on a device. And so this ticks some of the boxes that we're talking about here, but not all. So for example, the carbon footprint is going to lower because all the inference time costs can be shifted out of the data center onto the device. More importantly, the brittleness I referred to before, whereby if you're a robot or some sort of complex device that's intelligent by virtue of a model residing in the data center, but you're subject to the, if connectivity goes, the intelligence of the device, it completely disappears. Or if the latency increases, its ability to react to the environment suddenly diminishes. But if you're running your model entirely at inference time on that device, that device truly can become smart. But it doesn't tick all the boxes. For example, we still need to train these models in the data center. Largely, they're going to be driven by these curated data sets still too. There are a few other alternatives in the world of machine learning. So people have been experimenting with self-supervision, but this is very kind of, and there's a few extreme types of learning that seem pretty exciting. So one example I'd point to is some folks have been looking at doing self-supervision based on data arriving purely at the device itself. And so that you can imagine devices that learn just from the arrival of data, but in an isolated fashion. And so one of the problems, though, with that is that it'll take a long time for the information to accumulate in a single device for it to do things at the level that we expect them to. And you're really, you're limiting your ability to learn from all the other examples that single device hasn't seen. And so there's a laundry list of exciting types of learning out there that we could talk about that might be able to address some of these concerns. But when you analyze them, at least today, one of the key problems is the accuracy gap that exists. They're not able to provide us with the level of accuracy that a data center-based solution can give us. And so for that reason, they're a bit of a non-starter as of right now, or they can be exciting later on. But one area of technology, one direction that I think is extremely promising is that of federated learning. And when I think about federated learning, I'm not so hung up on its current form, which has certainly a number of limitations. But what I think is most exciting is just the general area of decentralized machine learning. And within that space, the most mature sort of instantiation of this is federated learning. And so we've been focusing on federated learning for now, but we're sort of opening our eyes to anything else that might emerge or some things that we might be able to invent. But what I want to do in the rest of this talk is explain how federated learning is very exciting, how it can address many of the limitations I've talked about in the earlier part of this talk, and discuss work that we've been doing to try to overcome some of the hurdles that prevent it being adopted more broadly. And so before I move forward, let me just very briefly give you a single snapshot view of what federated learning is, and in particular, how it contrasts to a data center style of learning. And so here we have an illustration of federated learning. If you just sort of focus on the illustration on the right of the slide, what it shows us is two main phases of federated learning. So phase one is when you have a series of clients Now, these clients can be individual institutions. So you could think hospitals, you could think of governments, you could think of lawyers' offices, or you could think of smartphones. So the independent clients within a network that each have some data. And what federated learning does at a high level is says to these individual clients, train your model on the data you have available to yourself. And then individual models that are then trained across the sort of number of different clients then are sent to a central server where using different types of mechanisms, they can be aggregated securely. And the key point here is that you want to integrate the isolated learnings of a various number of clients or various number of devices together so that the end result, the end single model, if you're trying to train a single model for all, is that it approximates what would happen if you would just end up uploading all this data to a single place and training conventionally. We want to be able to have a model that starts to approximate that. And so a number of nice facilities available here if you train in this manner. One of them being, or the primary one being, that the data doesn't have to leave the device. And you can leverage that property perhaps for privacy, if that's your main objective. Or you can also leverage that to overcome other types of issues. Say if you've got a legal requirement or a policy-based requirement that says data can't leave a hospital, then you can train with federated learning and be able to adhere to legislation that says data cannot leave. You can also have loose coalitions of perhaps even competing institutions. Imagine car manufacturers who, of course, for the benefit of society, would like to have the best type of model for doing lane detection, but for business reasons cannot collaborate. And so then they can enter this federated learning style of paradigm where the data is shared across all these different competing car manufacturers, and the resultant model can benefit from all the data between them, but they do not have to share the data explicitly and potentially leak other sort of business sensitive information. So there's many interesting, important characteristics. And so if we compare this style of learning to that of the data center version, you can see this major difference being that in the area of a machine learning data center style of learning, the data needs to migrate from the clients to a central place where a conventional style centralized training can occur. And so that's a very quick primer on what federated learning is. I'll be focusing also on this talk mainly about classification tasks that are a bit more familiar to all the different types of tasks we're trying to use machine learning to perform, things like object recognition, things like speech recognition, and so on. But it would be fairly simple to have a parallel talk from this point forward and discuss how you can use some of this technology to do analytics. So you could think of doing queries or other types of analysis on the data in a similar fashion. I just want to point that out to folks. So where are we right now with this area of federated learning? Well, if you haven't heard of it before, it's at a very interesting sort of point in its evolution, because there are examples of federated learning being used by millions and millions of people, by some of the largest companies out there. So folks like Google, Amazon, Apple, they all use federated learning for a few of their services. And so the classic example that you hear discussed is that of the Android keyboard, where the things like next word prediction are driven by a model that's learned in a federated learning mechanism. And so that's important because we can have good, solid next word prediction that does not require Google to see everything that you're typing on your phone. But what's an important limiting factor here is that if you look at all the different types of examples of federated learning being done by these large corporations, so things like next word prediction on their keyboard, hotkey word recognition, and maybe tuning to do with accents and some forms of ASR, recommendation of settings of different kinds on devices. What you see is that there's exciting applications, even some being deployed at scale by a few organizations. But if you think of most of the exciting, attractive things that people are talking about in the world of machine learning, almost none of those things are being done with a federated learning paradigm. They're all still being done in a centralized manner. All of these breakthrough methods that people talk about, doesn't matter what it is, if you see it on Twitter, if you see it being talked about on the net, the underlying mechanism, the underlying thought process is a centralized training method. And so there's a big divide. Federated learning is not being used currently for anything that exciting. And so largely niche things are being done. And so while it has huge potential, there's trials, for example, in the UK, there are small scale trials of how the NHS, which is our hospital service, so nationwide hospital service, can use federated learning to improve its modeling without sharing data between institutions. So people are starting to explore this, very seriously, but there's a big gulf between its potential and what it's being used for. And importantly, all the kind of quote unquote important forms of machine learning, the most exciting things, are not being approached with a federated learning approach today. And so the reason for that is there's a long laundry list of challenges that we've been trying to tick off. Because we believe once we can address many of these challenges to adoption, we can enter into an era where federated or various forms of decentralized learning can become much more mainstream, and whereby when people come up with an important new type of machine learning task, an important new type of model, we want to reach a point whereby they can explore that or deploy that in a federated learning method without spending decades in a centralized approach. And so some of these issues are to do with most of the federated systems, that almost all of them have this dependency that they're only being built thus far on regular labeled data with heavy supervision. There's a lot of issues to do with non-IID-ness. And so, and this is where most of the academics spend a vast majority of their time in terms of federated learning. They're thinking about how do we deal with the fact that in a centralized paradigm, I've got great control over how do I create my batches, how do I do my learning, because I have access to all the data. So I can formulate the batches of data in a nicely formed way with perfect characteristics in terms of what the learning algorithm is expecting. And when I enter this federated learning place and paradigm, all bets are off. The clients have to learn based on what data happens to be available to them. And that's going to be subject to user behavior or demographics of who happens to live around the hospital, or a variety of factors that are completely out of control of the machine learning data scientist. There's also issues to do with communication. If you just imagine the amount of effort that goes on in a data center to make sure that the GPUs are communicating at ridiculously high speeds, like either within a rack or between racks. Again, when you enter this distributed land, all bets are off. Individual clients are going to be communicating over potentially cellular links. Those links are going to even break. Clients are going to come in and out. And so the reliability and the speed and the resources that we enjoy in a data center completely evaporate. And so we have to find ways that are radically different for us to bridge that sort of gap. Those are three kind of different categories of problems that, again, really limit where federated learning can be. And that motivated us to develop an open source toolkit that we wanted to use to accelerate progress in the direction of federated learning. And so I think the way to think about this toolkit that we call Flower is to think about where we were back with deep learning before we had nice toolkits and tool chains and so forth that allowed us to describe interesting, new, exciting types of models and then have high performance training of those against GPUs. So we had things like so the same way that PyTorch and TensorFlow today enables it to be relatively simple to explore the design space of deep neural nets, we want Flower to enable people to explore fully the design space of federated and distributed forms of machine learning as they try to develop, the next breakthrough method, and do that in a way that abstracts away from them as much as of the heavy lifting as possible. And so this has been a community we've been working on for a couple of years. We now have 30,000 downloads of Flower every month. We have annual summit where we invite people doing work in federated learning and also users of Flower to discuss where it's going and shape what are the types of facilities that are required by the community. And so the rest of this talk, I want to talk about work that we're doing with Flower and Flower itself as a tool. And of course, I'm doing the speaking, but the heavy lifting and all the great ideas and work have been coming through folks you see here. So these are the core contributors to Flower, the original set of people. Some of them are from companies like Nokia. Others are from other universities like Oxford, Avion, but most of them happen to be from Cambridge in my group. And so I just want to acknowledge them. So the rest of this talk is going to be one part, a bit about the framework. I'm going to touch upon one particular type of technique that is particularly useful. And the rest of it is going to be a series of case studies that I think surface some of the exciting parts of the federated learning research area that can be enabled through Flower. And in their own right, I think they're kind of interesting vignettes of what we've been up to. I mentioned before that we want to make it easy for folks to explore appropriately the design space of federated learning and sort of not worry about some of the details. And so one of the details that we think people ignore too much is how will their techniques work at scale? And so this figure that you see on the left-hand side is recent papers in the area. Each of the blue dots are recent papers. And we looked at when it comes time to evaluate their technique, if they want to see how fast their sort of interesting type of aggregation strategy is going to work, or some sort of other type of method in the federated space is going to function, they need to make two critical design decisions. How many clients are they going to consider in their client pool, in terms of scale at least? So how many clients are they going to use inside their client pool? Is it going to be a federation of hundreds or thousands or tens of thousands of clients? And when they do the learning round, how many of those are going to be involved? And what we found is that although most people are being motivated by this large federated systems that are potentially IoT devices or smartphones, or maybe hundreds of thousands of different locations worldwide, when it comes time to evaluate their algorithm, most of the time they're focused on a scale of a couple of hundred clients and maybe tens of clients being learned at every round. And for some of that reason is to do with the difficulty it is in scaling up. And so as a preview, on the top, on the far right and far top, you see this green dot. And so this is an example scaled experiment using the Flower framework, where we're involving 1,000 clients per round and 15 million clients in total. And we're able to simulate that with just, I think, around 4 or 5 regular GPUs in a data center. That so regular scientists or academic institutions could have access to that type of GPU resource to simulate and see how well their method is going to work. And so I'm going to be skipping out a lot of the different components. So I think we've got some important facilities about how you can develop new types of differential privacy. We have some interesting methods that allow you to explore things like device heterogeneity and doing benchmarking, fair benchmarking between different techniques. But I'm just only going to focus on the scaling aspect and explain very briefly how do we allow people to simulate at that large scale. So I'll just skip this slide and show you a couple of illustrations of the scale. So this left-hand figure is a more detailed analysis of what that experiment was. And so to show that experiment with a few lines of code, we took the Amazon book review dataset and we showed that you could parameterize this in any way you wanted. That dataset is 15 million different reviewers. They're each providing reviews of their books. And we want to show that you could train a model to predict their reviews at a scale that would be otherwise difficult and is not really seen anywhere else except for some of the experiments presented by Google and Apple and so forth. And so this figure on the left is more like an example proof of doing experiments of this kind on a particular data set that we just happened to download and started the training process. And you can see as you vary the number of clients, you can see the learning is working. So it's more just an example of how well the scale can materialize. On the right-hand side, I want to show you another dimension of scalability. And so this is a comparison between the scalability of our framework and a few other alternatives. And so while these alternatives are extremely useful for different reasons, so depending on what you're trying to do with your federated learning, they might be really valuable. But when it comes time to analyze how well your technique is going to do when you're scaling up the client number and the client per round, it looks to us that flowers is the better choice. And so this first experiment here that I'm showing you is against FedJax. And so FedJax is an alternative offered by Google where it's scalable. One of the reasons why it's scalable is that instead of having a fully fledged deep learning framework underneath, it has the JAX facility for training and specifying models. The trouble with that is that if I want to use some other model, say if I want to federate some exciting new technique, I have to re-implement that in JAX. The positive is that it provides me with quite a bit of scalability. As you see here, we have a small experiment with 3 clients with one learning local learning epoch during the training process. And you can see that Flower is a lot longer than FedJax. But what is interesting is when you increase the complexity of the experiment. So for example, if we do a little bit more heavy local learning on each of these clients, you can see that FedJax starts to slow down quite a lot. So not only are you losing the flexibility of being able to take an off-the-shelf model and use it within the same learning framework, because Flower, as I probably didn't mention, Flower supports any type of learning framework. So you can use it with PyTorch or TensorFlow or so forth. Not only do you lose that facility, as you increase the complexity, things like FedJax starts to slow down. And I'll explain why in a couple of slides. If we look at other alternatives, so if we compare Flower to things like TensorFlow Federated, under the same setting with a slightly more ability to have more complex conventional style models, you can see under this setting, TensorFlow Federated is also quite a bit slower. And so we can see this trend go on. And the reason for this is that within Flower, we've built what we call the virtual client engine. And so the way to think about the virtual client engine is that it solves a similar problem to when you're doing distributed training. What we want to do is in the simulation phase of Flower, we want to maximize the throughput and the resources of a set of HPC resources. So a number of GPUs that a researcher might have under their desk or in a rack in their server room. And what we want to do is maximize the utilization of the GPU memory and the throughput through a network series of GPUs to simulate a large federated system. And so to do that, we have a series of a couple of important facilities. One is something we call virtual client proxies. And so what that means is that we look at the federated learning workload. So you might have some specification of a model, a series of clients. You have some learning types of parameters. So you're saying, for example, how many clients do I involve in a certain round? And what our system does is come up with a schedule and that instantiates the clients that are needed on the GPUs when they're needed. And because under federated learning, most of the time, clients are not being used and they're only used when they're needed within the sampling round. And so by scheduling these clients and instantiating them when they're needed, and also allocating clients across the different GPUs so that you're maximizing memory, you can radically increase the throughput of the training speed of when you're simulating these workloads. So it's very similar to doing distributed training, but there's a number of aspects of federated learning where where it differs from conventional centralized learning that methods currently existing sort of start to not support. And so we've come up with a series of ways of doing this scheduling, doing this allocation, and quickly tearing down and bringing back up these clients that enable the type of utilization that I've been showing so far. Another important dimension to this is that when it comes time to more carefully analyze things like resources, you can also include real devices. And so we can have mixtures of what we call virtual clients instantiated within a GPUs in a conventional HPC, working alongside real client devices, things like a Raspberry Pi, things like a robot, to provide you with a full simulation of all the different types of parameters within your design space when you're assessing how well is your system really going to work. And so just to summarize, not only does I've mainly focused on the scalability of Flower, but there's a number of other dimensions that I'm ignoring here, just for the sake of time. But it allows you to do things such as examine the sensitivity of your method against system resources like network and wireless and memory and compute. It allows for systematic comparisons between different type of techniques. So that when I was showing those comparisons between different FL frameworks, there were really turnkey comparisons where you can see just in that case, what was sort of the throughput of doing simulations of different kinds. And finally, I've talked a lot about simulations, but the system also allows you to bootstrap new types of applications. So if you want to test out something and then decide you want to launch it and explore the application space a bit more thoroughly, you can do that all within the same system. And so what it means is that as you start to examine different types of research problems within the federated space, it's a really powerful engine for being able to do that very quickly that currently has been absent in federated learning up until this point. And so now briefly, I'm just going to touch upon very quickly a couple of case studies. Each of these case studies have an interesting sort of add an interesting part to the discussion about federated learning and how we can push it forward. And then at the end we can have some questions. The first of these is to do with speech recognition. About a couple of years ago when we started looking into this, we realized that there hadn't been much work on training full-scale speech recognition models. So not hotkey word recognition where you're trying to recognize a small vocabulary of tens of words, but when you're trying to recognize tens of thousands of words with a conventional ASR model and training that model using distributed data. And so when we first looked into this, there was only 2 or 3 papers doing this, and most of them had done federated learning in a way that I think obscures the core issues. And so they had analyzed their federated system using library speech or data sets like that. And what we realized is that because data sets of that kind, library speech, and as an example, had been collected in very controlled settings, as you divided, in this case, library speech between different users to proxy what it would be like in terms of getting data contributions from one user here, another user there, because they were all collected in very similar acoustic environments, it lacked core properties that you would find in a federated system. Namely, if you really were doing ASR learning with samples coming in from a number of different locations and clients, there would be acoustic background variations that would be present in those streams. Also, obviously, people would speak very differently. And then there would be there'd be class separation where some people would speak, it would say a few, a subset of the vocab that you're expecting to see, another group would see another subset. And so there would be sort of potentially definitely different distributions of classes in the data set. And none of those characteristics were present in library speech. And so we had to search out for another data set that we could tidy up and formulate into something much more aligned with that of federated learning. So we used actually the Mozilla Common Voice dataset. And so what this figure illustrates here, if you just focus on one illustration, if I move my cursor here, just for this one here, this is showing the acoustic sort of complexity, where if you look at the different speakers saying similar words, this is a, what it illustrates here is that there's a lot of overlap in the classes that have to be sort of modeled. And so while library speech on the left-hand side is a much simpler environment where the class separation is nice and clean, Common Voice, because it was collected from real users who were physically in different locations contributing data through their laptops. So this was a data set collected by Mozilla. what it is far better tuned to the kind of issues that you'll face with federated learning. And so as we moved, once we had this data set in hand, we started to look at what would it take to train various kinds of ASR models. And so I won't go through the details of the solution we eventually came up with, but essentially we came up with a recipe, if you will, of how you can train a state-of-the-art architecture, so encoder-decoder architecture that was commonly being used in many of the near state-of-the-art ASR models, through which we applied a series of tweaks that would enable it to converge under a federated setting. And so one of those key, or the two key tweaks I would mention, one is that there's a warm-up phase where we have a tiny amount of centralized learning necessary to help the model converge much faster than normal. And second, during the aggregation phase, we're taking into account the word error rate more explicitly, that allows the system to work. And so as a result, we're able to come up with results based on Mozilla that we think are some of the first results that show that it's possible to train a full-blown ASR system under true federated learning conditions. And this was enabled through the flower approach. And so I'll just point out the word error rates here. So if with this particular task, the best you could hope for is that you would have word error rates that are getting close to a purely centralized setting. And so while the word error rates maybe look a little high to you, they're in around 20%, we're able to show that the method that we're able to sort of empirically design is able to get to levels that are very similar to the centralized approach. I'm going to skip the next case study because I want to tell you about the last one because it's very exciting. So let me just move down to this method. Yeah. So I'm going to tell you about the last case study so we have time for questions at the end. This last case study is focused on self-supervised learning. And so I'm a big proponent of the potential of combining federated learning with methods that are not so attached to learning through supervision. And that's because most of the systems and applications are going to be difficult to have the user contribute truly labeled data. So while in federated learning and distributed learning examples, it's very obvious how you can collect lots and lots of data. So if you have a doorbell, it's going to have a nice camera stream you can access. If you have a smartphone, obviously it's going to be able to capture lots of audio. But what's going to be difficult is getting that data labeled. And so if we can bring these two worlds together, so various forms of self-supervision or unsupervised learning combined with various forms of decentralized, distributed forms of learning, that's going to be a very powerful recipe. So that was our motivation to look at one of the first examples, I believe, of using self-supervision to train a video understanding model under a federated learning system. And so I'll just highlight the authors here because this was a collaboration with TCL. So I want to highlight those folks. So they really brought on board the video understanding knowledge. We brought on board the federated learning and systems methods. And so we developed a technique that was actually shown just last week at EECV. This is a method that we call Fed-VSL. And so Fed-VSL seeks to train video understanding models. And you should think of this primarily as a proof of concept to show that you can do this under federated learning constraints. And so if you haven't seen self-supervision before, the style that we're applying here is this one where in the unlabeled phase, what we're trying to do is train an embedding. And we're doing that through a series of pre-tasks. So pre-tasks are training the embedding to do well, tasks that we don't particularly need, but for which don't need supervision. So you could imagine, for example, a video whereby you permute the order of events, and then you train the model to have the right order. And you know the right order because you have the original video clip. And so there's various other kinds of pre-training tasks that already exist within the video understanding literature that we reused. So another one would it be when you obscure a part of the image of the video and you ask it to maybe rearrange to fill in that missing gap, or any of these types of pre-tasks where you're able to understand what the ground truth should be, but you don't have to label it. And so once you train the embedding to do well on these set of pre-training tasks, the next step is to take that same embedding and with a small amount, ideally a small amount of labeled data, train it on the task you care about. And so this downstream task portion, we experimented with action recognition. So that is sort of recognizing what a person is doing inside a video clip. And so that some of those examples are shown at the top part of the slide. So I'm going to just sort of highlight my cursor here. Labels such as applause, bookbinding. So fairly complex types of actions being understood through video. We also looked at a secondary task of a video clip retrieval. But the main point here is that what I've described thus far is a conventional way of doing building video understanding models with self-supervision. But what we did was develop a method that enabled this to work in a federated learning paradigm. And so we had to overcome, for example, overheads of data exchange between the clients who are learning these pre-training tasks, and then the server that was doing aggregation of these models, and then later downstream task training. We had to look into how the aggregation would work differently. So there's a variety of methods that we designed. The two main sort of contributions here was distributed system design that enabled this all to work with relatively low overhead. It became feasible to exchange the data necessary to build these video models. And then second, at the video aggregation stage, we introduced a new way of aggregating the models so that convergence was good. And so I'll just show just one slide of results. So we did these experiments to look at a variety of different things. We wanted to look at, for example, what were the manifolds for learning under centralized versus federated, because there was a few differences there that we didn't expect. But one thing we did find was that through this method, the accuracy could be sufficient for actual use. So we found we could generate accuracy levels for doing things like action recognition and video retrieval at levels that were the same, if not even slightly better than centralized methods. And so I can just quickly show you in this particular table here, the centralized baseline is the top, and then below it are various variations of doing a federated approach. And then the bold as convention is showing us the best results in the table. So if you look in where it says fine tuning and linear probe, those are two different forms of doing action recognition in the setup of the experiments. And you can see the best results were under a particular configuration of our federated learning solution. So it was very exciting. And what I think is probably perhaps the world's first results of doing video understanding under an SSL setting, and doing it in a federated learning manner. So very exciting sort of proof of concept results. And so that brings me, oh, that was the error. So that brings me to, I've only talked about two of the case studies. I want to move to the part where we can start to answer your questions and we can debate some of the things I've raised. But before we do that, I want to leave you with a prediction. And that is, I believe that given the rate of progress that I see in the area of federated learning and the rate of progress in methods like self-learning, I think we might reach a stage in a few years' time where there can be quite a dramatic change in dominance. And so right now, if we build IoT devices that do simple types of image understanding or video understanding or audio understanding, systems of that kind, they are always trained right now through first training a big model in a data center using a static data set, and then deploying that model onto a device. And so you might think of an example being a doorbell, an IoT doorbell. And so those devices now recognize a face, They might tell you when someone's outside or not, if it's a person. My point would be that right now, the data center dominates machine learning. But I believe that this type of system might be the canary in the coal mine to show us an example of a federated system that could be commercially viable, whereby the data center starts to lag behind. And the reason for that is that there'll be a series of unfair advantages that federated learning will start to accumulate. So for example, as we get better at self-supervision, we're going to start to have the ability to train these models using in situ data. And so we will no longer have this big domain shift between the static data and the data that's being observed, for example, from the doorbell. The faces the doorbell sees every day will be the faces that drive that model, and versus the faces that the data center based model will be, a collection of faces that may be, not representative of the faces that it sees as it operates. Furthermore, as we get better at self-learning, self-supervision, data center versions of those systems are going to start to lag behind because of the difficulty in shifting all of that data from the edge to the data center. Whereas if you have a system that's based on locally consuming this information and improving as it arrives, it won't have this sort of bottleneck of data transference. And so we can unpack that with further questions as we go on. I just want to make this prediction as something that we can further talk about. But with that, I am happy to take questions from the audience. So thank you for your time.
Thank you, Nick. We have a couple minutes for questions. So if you have a question, feel free to click on the raise hand button in Zoom, and we will call on you in the order received. So Nick, maybe I can start. Oh, actually, we do have a bunch of questions coming in. Sushant Prabhu has a question. So first of all, Sushant, if you want to ask a question directly, you can actually just unmute yourself. Otherwise, I'm happy to.
I see the question, so I could just start to answer. But Sushant, if you unmute and you could also engage. But I just see the initial question is about how do you address the security concerns coming up due to FL, and then so one thing I'll add to this discussion, because it's a big topic area. And I think it requires, obviously, security experts to really understand it, something that I'm not. But something that I do see is that many of I think depending on what the application is, it is possible to engineer a system to meet the needs of these specific applications, depending on what they are. And so what I mean is that we might have security weaknesses that people observe in the literature that require certain assumptions that are not always going to be commonplace in the applications that we might want to roll out first. And so some of those security assumptions are that people understand all the parameters of the model, or maybe they assume that there's some ability to arbitrarily inject as much data as you want. And so these types of concerns can be addressed in various kinds of closed forms of systems. And those are the types of systems we can roll out initially. And that's just one observation I make on this topic. But generally, there are a lot of issues to be examined in the security space. The other thing I would say is even if a system might be insecure in terms of not being able to maintain user privacy, there are many forms of federated learning that are useful even without those being available that I've noticed. So one of these things is to do with being able to train otherwise inaccessible data. So many data science projects can't get off the ground because you need to have an awful lot of trust between all these different participants. And so if you can allow them to weekly collaborate, and perhaps there's a bit of data leakage between them, but they're able to hold on to their data and not enter into the sort of a situation where they have to all give it to a central party, then these data science projects can take off and start to become, they can find the utility from them. So I guess my point here is that even though we might not have watertight security, there are some interesting applications of FL that can come downstream that sometimes are being ignored.
So if there's any follow-up questions. Oh, so Sushan says perfect. All right, let's go to the next question. Nick, do you want to read off the next one? Should I?
Sure. I'm just going to paraphrase it. I see, I did an interview, who felt the way through the problems with data centers was by innovating the efficiency of the data centers themselves, changing the storage medium, et cetera, et cetera. Do you think the industry is broadly moving towards solving such problems with distributed learning, or are there multiple camps here? I guess I'm a bit confused by what you're asking. Maybe Fred might better help me parse it.
So I think Jackson is asking about whether tackling some of these approach could be by improving the efficiency of data centers themselves, as opposed to innovating on the federated learning aspect.
Well, I mean, definitely that's happening, and it's going to continue to happen. So making data centers more and more efficient. But there are some sort of building blocks that are fundamental to how they function. And so one thing that's going to be very difficult to overcome, for example, would be, how are you going to move all this edge data from the clients to the data center? And so the only reason why I think that's one of the most important key watershed moments is if you imagine as we go through time, and you imagine like the increase in our ability to leverage unlabeled or weakly labeled data, as that increases, I think there's going to be an opposite direction of the utility of data centers and the need for more and more local learning. I think another way to think about it is, think of a spectrum whereby you're saying, how much work are we doing on the local side? How much information is being extracted from the information that's passing by locally? And then how much do we leave for this information to be extracted centrally? And so as we are able to learn from data locally more easily, whether that's just the ability to do it, or perhaps even as we get better at it, the sample efficiency of doing so, as that increases, the pressure in many of these systems to learn locally and have a distributed form of learning will just increase, because it'll just be, you won't be able to shift all of that data from the edge to the data center. So that's like one example of, doesn't matter how fast the pipe gets, if we can do data processing locally, that's going to be an insurmountable sort of advantage.
I assume there's also the privacy issue, right? Sort of, there are just a lot of data that people do not want to shift on to the cloud.
Sure. Yeah.
All right. So I think we are approaching the end of the 1 hour slot. So with that, I want to thank our speaker, Nicholas Lane, again, for this fantastic and thought-provoking talk. And thank you all for coming to the seminar. So remember to visit Nick's website, and also flower.dev. It's a fantastic federated learning framework. All right, thank you, everyone.
Thanks very much.
Thank you.